Okay. Hello to everyone. And today I'll continue with the zero knowledge for classes of languages from that we looked last time for statements involving one-way functions, homomorphic one-way functions, and the language will be of values in the function range. Which are in the function. So in values in the function range, which are images of some points in the domain under this function, right? So if the function is onto, then everybody in the range is satisfies this statement. But we have seen examples where it's not trivial. Not everyone is onto. Right? I mean, this function, for example, is not an onto. It's you only values in the range which are images of the function are essentially correspond to Diffie-Hellman tuples. If you think of GH as a parameter of this function, and if H was randomly generated, and we have seen that some practical languages map to this. We have seen that this the intuition behind the graph isomorphism zero knowledge proof extends to this type of languages, and but it's actually these type of languages allow for something stronger. So last time I was only arguing the equivalent of the same statements that we made for the graph isomorphism zero knowledge proof, which was that a single instance of this three-round proof is zero knowledge, but it has only 1/2 soundness error. So a malicious verifier, malicious prover can still pass it with 1/2 probability, even for y's which are wrong, right? Which are outside of the image of the function. So to get negligible soundness error, you have to repeat this security parameter number of times. Okay, so now let's see that you can do it better. Okay, so so today I want to do the following. That basically zero knowledge proofs for languages of homomorphic one-way function images, which really occur quite often in cryptography. Okay, so of course we'll study whether you can do zero knowledge for any NP language, right? Because perhaps some languages cannot be mapped into this. So everything I'm saying now is not very useful if that's the language you have. And there are applications of such languages as well. But many languages in crypto, okay, like that you have escrowed something that was correctly corresponded to, it was really your secret key corresponding to some public key, or that you have re-encrypted some credential and the credential verifies under some public key, but you're hiding this credential, so it's only encrypted or committed. All these languages have a hope, at least, to be mapped to this type of class. And if they are, then everything we're saying applies. So in particular, you get zero knowledge for such languages essentially at the same cost as even like creating a statement in this language, which is very attractive. So, okay, zero knowledge for these type of languages, which are as efficient to prove and verify as creating as basically computing this one-way function and therefore creating the statement. Okay, so proving that you have escrowed something correctly is basically like as expensive or as inexpensive as just creating the escrow to begin with. Okay, and technically what we'll do, we'll introduce the concept of honest verifier zero knowledge. So this is a relaxation. So we'll create something that is less secure than a zero knowledge proof. However, it will these honest verifier zero knowledge proofs will have some special properties involving both honest verifier zero knowledge and soundness. And these properties are called sigma protocols. This is a kind of funny name. It was given that name a long time ago. And this is just stands for certain class of these honest verifier zero knowledge proofs. We'll also consider, at a term of this would be another term is also public coin zero knowledge. This would be in particular that class will fall into this one. And of course, the reason that we want to do it is number one, that this the homomorphic one-way function image language has this sigma protocol. In other words, it has the honest verifier zero knowledge proof. So these languages have sigma protocols, and why do we care? Because we'll show compilers from sigma protocol for a given language to, well, first of all, non-interactive, so extremely attractive, right, from communication and usability point of view, zero knowledge proof, so no longer just honest verifier zero knowledge, so no longer the relaxed class, but the fully usable and secure class for L, for the same language, but in a random oracle model. Okay, so we'll use a hash function model as a random oracle, and this is called the Fiat-Shamir heuristic. This methodology. But that's not the only thing you can get. Also, the 3-round zero knowledge proof for L in CRS, so common reference string. So you don't need to trust a hash oracle, but you do have to trust some parameters. And of course, what you would like is to have, and the point is that the cost of of both of these and the cost of A and B are essentially the cost of the sigma protocol itself. Okay, this will be completely true here because all you add is a bunch of hashes. Here you do need to add some public key stuff, but not much. Okay, so of course, we would like to not trust and to be people to be able to prove in zero knowledge without idealizing hash functions as random oracles, and without trust in a common reference string. But unfortunately, we don't have efficient. I mean, we have the practical schemes that come out of here. I don't think we have results without. Okay, you know what? I might be wrong. So perhaps there are compilers who actually don't assume this. They will for sure take more rounds, because in a plain model you cannot have 3 round zero knowledge. Essentially, argued in the black box way for non-trivial languages. And yes, you have zero knowledge with more rounds in a plain model. The question is, do you get an efficient one, as efficient? Do you get this type of statement for the result C, which removes this? And that I'm now forgetting whether that is true or not. Of course, it's an important question that I should know the answer for, but I don't remember right this minute. Okay, so this is the plan. Okay, so what is honest verifier zero knowledge? A proof system PV for language L is honest verifier zero knowledge, HVZK, if there exists an efficient simulator such that, and instead of the full zero knowledge, which said that I have to simulate for every verifier algorithm, including the one that cheats in the way it interacts with the prover, I will now show zero knowledge only for honest. If the verifier follows the protocol, then their view is indistinguishable. So the simulator basically such that the distribution of randomness of the verifier and the view of the verifier that are output in a randomized way by the simulator. Well, in the very least, it has to pick the randomness of the verifier uniformly. By the simulator on input, the statement in the language, and that's it. So this will hold for every X in the language, that this distribution is indistinguishable from the distribution randomness of the verifier and the view of the verifier that are created as, well, randomness of the verifier is chosen at random from randomness space of the verifier, right? So any proof system, the verifier has to be randomized in a zero knowledge proof. I don't want to say a lie, so I don't remember right now, is this for sure true, but I think so. Okay, so let's bracket this, but I do think that verifiers have to be randomized to get zero knowledge and soundness for non-trivial languages. Okay, so whatever that space of randomness of the algorithm V is, RV is just chosen at random from it, and the view of V is created in a randomized way from the interaction of the prover who has the statement together with the witness, and he interacts with the verifier on the statement, and the verifier has this randomness as its side input. So this is verifier's randomness, and maybe we can denote it like this. So this is a view of the verifier from this interaction. Okay, so it's a special purpose notation where we put two algorithms interacting, we specify their inputs, and but we only care about the view that this guy gets. Okay, so in particular, we don't care about the randomness of the prover. What is the randomness over? Well, actually, this is exactly the randomness of the prover. Okay, and this is the witness. We don't have the witness here, so I have to also go over all witnesses W for X in L. In the case of these homomorphic one-way function images, languages, well, actually, even there, it is not necessary that an image of a one-way function has a single pre-image, but if this is a group homomorphism, then I think that probably implies that. Although yeah, it should imply, if it's a group homomorphism, that there will be no collisions. But maybe that's not true. I'm not sure. Okay, so yeah. Okay, this is and where is the difference from the full zero knowledge, right? So the difference is that the delta from zero knowledge is that we only consider algorithm V and not any efficient attacker V star. Okay. So in the full zero knowledge property, the quantification goes over every efficient verifier V star, every efficient cheating verifier V star, and the view that we consider here in the real world is one between the honest prover and a possibly cheating verifier. Okay, so this simulator has a sort of easier job. He just has to match the view of V, and therefore we don't, yeah. Okay, and V is designed by us and not by it's not an arbitrary algorithm. Okay, now what is public coin proof system? That's simple. It's a proof system where verifiers' messages actually it's only one. RV, verifiers randomness. Note that all the proof systems we have seen for graph isomorphism or this homomorphic thing were public coin proof systems. This is not necessary. So the only thing verifier does is he sends random coins. Okay, he doesn't take randomness and do anything local with it, like encrypts it, commits to it. okay, which we will see actually can give verifier power, and there are examples where that can be used to make while basically to get soundness, right? Like if the prover is in the dark about what this guy is doing, perhaps it's harder for the prover to cheat. Okay, so we'll see examples of this, but so far, the zero knowledge proofs we have seen are public coin, and these are because okay, the only case of such I have seen is 3 rounds. So these are three round proof systems. As indeed right, so the prover sends the first message, this guy sends essentially randomness, prover responds, and the verifier has to now decide. Although I guess you could think of a 2 round system, right, which the verifier just sends randomness from the get-go, and the prover doesn't commit to anything. And this guy has to now decide, accept or reject. Okay.
Professor?
Yes.
So the idea is that the verifier leaks the whole randomness, and so that's the only message it needs to send?
Yes.
And the prover would be able to simulate any other messages. Okay.
Yes. If he's honest, if the verifier is honest, so if only you're considering honest verifier zero knowledge, in yes, the previous lecture we considered full zero knowledge, where we didn't say that the verifier really just sends, I mean, that the cheater sends his randomness. Maybe perhaps he computed this. That's why we had to, in the simulation, we had to send and see what he output. And if that was wrong for us, we had to recurse. We couldn't just give him, you know what, please output this following B, because that's convenient for me, it's a simulator. You can see that basically honest verifier zero knowledge will therefore be much easier for these proofs. And two more sort of technical properties. So special HVZK is that it's just a technical property which these proof systems have, and this same technical property makes this argument easier, this compilation, and this argument easier. Perhaps relaxations in these properties still allow both of these results, but we mentioned that the relaxations actually are important, for example, in RSA setting, where things don't work so neatly. But right there, it's clear that these type of results for RSA crypto systems indeed are worse. So this efficiency claim is not quite right. You get worse soundness, you have to repeat more times, and so on and so forth. So, but it's it's sort of like tangential for us right now. Okay, so special HVZK, what is it? It's a special requirement on the simulator. The simulator here has just a statement in the language as an input. We're going to strengthen it and say that the simulator takes x, RV as input, and view V, which is produced by the simulator on the XRV, is actually identical, identically distributed identically as the view V that results from this interaction. So prover XW and verifier on X and RV. Okay. Okay, there's no close bracket here either. So this is a distribution that came out of the honest conversation, right? And the distribution produced by the simulator here as well. And this has to work, and this works for every X and in the language, and every W dot dot, right, which is correct for X, and for every RV. So this is the new thing. Why is that different? Well, here the simulator, perhaps he has some freedom by fixing the RV rather than having it as an input. And moreover, we only require that these two views are indistinguishable. So this is stronger on both counts. Okay. But clearly, sorry, it's not focused. Sorry about that. Okay. This special honest verifier zero knowledge implies this one, because if you have a simulator like this, then you have a simulator like that. This simulator just picks RV at random and feeds it to this guy and produces RV using this algorithm, right? And clearly matches these views because RV is picked at random before it's fed to this guy. Okay. Now, what's the special soundness of these proof systems? It is that for every, get now my notes not to mess it up. Okay. Okay. You know what? Let's do it on a fresh page. So special soundness. Special soundness of 3-round public coin proof system. Is like this. Okay, well, let's agree on some terminology first. So the prover has a statement and a witness, the verifier has a statement, and this is a 3-round proof system where let's just call these messages A, C, Z. Okay, so here X is a statement, W is a witness for X in L. A is called a commitment of the prover. That's the way the zero knowledge proofs are constructed. Like the A is in some form acts as a commitment of the prover to some random choices he made. You know, the two cases we have seen, graph isomorphism and images of homomorphic one-way functions, the commitment was a random point in the same language. And the pre-image, the randomness created in this commitment was the witness that this random point in the language is indeed in the language. Okay. The C message is called a challenge of the verifier. Okay. And indeed, that's what it was. It was a binary challenge. The verifier said, explain your commitment, your temporary commitment correctly, or explain it together with the statement as, correct statement in the language, somehow the two witnesses co-joined. Z is called response of prover to challenge C. Okay, and given this, the verifier outputs accept or reject. So accept 1, reject 0. And moreover, because it's a public coin proof, C is just random in some space, right? That is part of the algorithm design of V. Okay, so now what's special soundness? It is that for every statement, for every commitment, first message that the prover sends, and for every 2 different runs of the challenge response, call it the first CZ, and the second one C prime Z prime. The following is true. If C is not equal to C prime, so in the 2 executions, the challenge C and the challenge C prime, where the only thing that is true about them is that they're different. In the case of binary challenge, that the 2 cases we've seen before, the C would be challenge 0, C prime would be challenge 1. And the verifier algorithm on input X and the prover's message A and his own challenge C, so that's really the verifier's own randomness, and prover's response Z. So this is now the full transcript of V, right? The statement, the randomness here, and the messages AZ from the prover that he accepts on these. And moreover, that he also accepts in this alternative conversation, which had the same, prover started with the same message, but verifier in the alternative computation chose a different challenge, C prime. And the prover responded presumably differently, although maybe the same way, right? That doesn't matter. But the verifier accepted on this. If all of this is true, then X is in the language. Note the zero knowledge proof for graph isomorphism, let's see, and for language of homomorphic one-way function images, the 2 that we have seen so far both have this property. Indeed, this is how we argued soundness. We said, no matter what the cheating prover sends, no matter what his first message is, if it is the case that he can reply in an accepting way, that the way that makes the verifier to accept, both to challenge C equal 1 and C prime equal 2, right? Because there were the only 2 choices in these for the verifier's challenge. Then if the proper responses to both challenges exist, then there is some equation where basically A, this message cancels out, and what you get is directly that X is as a element in the language. So correspondingly, that there was some graph isomorphism between the 2 graphs, or that there was a witness which makes the statement F of the witness, right? The one-way function image. Okay. Okay, so let's now show consider an improved version of it is zero knowledge proof for this language of homomorphic one-way function image for some function f. Let's just call it LF. Okay, so this is the language of homomorphic one-way function images. Okay. Well, it's improved, but it's really apples and oranges, which is a 3-round public coin, honest verifier zero knowledge, with special honest verifier zero knowledge and special soundness. But with negligible soundness error. Okay, and we will see in a second why this statement for this new proof version has implies a negligible soundness error. Okay, so let's take the proof as a blueprint and see where the difference is. Okay, so we have to deal with the shift in the terminology that y, which is f of x, is a statement, and x is a witness. Okay, whereas in the generic terminology here, x was a statement. I don't know how to maneuver between these two conventional annotations in a smoother way. So okay, so the prover had a y and an x statement witness, and the verifier had a y and presumably f of y is f of x, sorry, is y. Okay. What does this guy do? Okay, he sends a random element from the domain and computes f on it. And now, instead of challenge C, which is just either 1 or 2, this guy will pick a challenge at random from ZQ, where, so we need to now assume something. Recall, F is a homomorphism between two groups, the domain group and the range group. So these are two groups. And because they're groups, so they have an order. So let's assume that D is an additive group. This is just a notation, but it is a notation. So whether we denote a group additively, the group operation is an addition, or group operation is a multiplication, this is just a convention. But it is one that maps to the cases of prime ordered groups, and the case where f is either exponentiation or a generalized exponentiation. So a function that takes a bunch of elements in ZQ and exponentiates them and multiplies them in some fashion. Okay, we see the symbol extension where there's two group elements G and H, and you take an X and you exponentiate both G and H to the same exponent X. So we'll assume that the domain group is an additive group of order Q, and we'll assume for convenience that Q is prime. But it's not just convenience of notation. If it's not prime, there is some issues, and that will plague RSA instances of this. We'll point out where this issue comes. And let's have a notation for R that it's a multiplicative group. And because it's a group of homomorphism, then it's of same order. Right, so this is implied by the fact that this is a group homomorphism. And recall what a group homomorphism even means. Homomorphic, the fact that F is a homomorphism means that for every x1, x2 in the domain, f of x1, and I will use now an additive notation. So this is a operation in the domain group, which I would denote additively, is a group operation applied to the images of x1, x2, but for the target group, I use the multiplicative notation. Okay. And moreover, so what this implies, generalization, is that also for every alpha, beta, which are just, well, they are, actually it works for any integers, not just integers mod q, that, sorry, f of alpha times x1 plus beta times x2 is f of x1 exponentiated to alpha times f of x2 exponentiated to beta, right? Because what a multiplication, just addition alpha times, well, so that corresponds to the alpha times operation in the target group. Same with B. Okay, okay, so we choose this from the order of integer, but modulo the order of the group. And what this guy outputs is not just either x or x plus x1, x prime, right? Because this is a plus, but a linear combination of x and x prime, where the coefficient in the linear equation is c. It could be alpha beta, but it doesn't matter if we do it fully like this. So let's just save some bandwidth of the verifier, because making it alpha beta doesn't improve anything. So this is x prime plus c times x, where this is an operation in the domain group. Okay, there is a well-defined multiplication by an integer, right? So that's what happens here, and you add in the group. So if the group is, if D is, so therefore, if it's of order Q, then basically D is the same as ZQ. Okay, so this would be just addition and multiplication mod Q. Look, this is a strict generalization of this. So if C is 0, then Z is X prime. So it's this case. If C is 1, then Z is just an addition of X and X prime, which is this case. But we generalize it now. It can be any linear relation. And V accepts if, well, how can he verify this now? Well, he applies the homomorphic one-way function to this response, and he checks that using this linearity, that it is f of the first one, which is y prime, right? Because it's supposed to be f of x prime. Now he has f of x, presumably, but that part of the witness, right, was multiplied by integer c. So we need to take this to the c's power. So these are all operations in the range group. Okay. So you have here this generalization of this proof system. And okay, let's completeness, well, goes through, right? It will always accept if just by these equations. Special HVZK. Well, it's the same simulator. Simulator, given the image, a value from the range, and given a challenge C, right? That's how the special simulator had to work. The special simulator was given the randomness as an input and a statement. So it's given the randomness and the statement. And it has to create a matching view. So what does it do? It picks Z at random in the domain D, which is basically ZQ, integers mod Q, and computes what? Y prime to match the verification equation. So, which is f of z times y to the minus c. It's an additive group, so minus is well defined. It's just minus c mod q. And so we can do this. And of course, if you plug that and yc, you can see obviously that yc and y minus c cancel out, and you get fz. So verifier will accept. Why is it matching exactly these views? Well, we are only concerned with an honest verifier who gets this statement and whose random coins are these C. Okay, now look that both in the protocol, y prime is a deterministic function of C, Z, and Y in an accepting conversation, right? Because put this on the other side, and Z, Y, and C all determine Y prime. So the distribution of Y prime is doesn't add anything to the distribution given Z, right? So when we look at the distribution of the views of the verifier, we can just focus on Z, because the Y prime part is the deterministic function of Z, of the rest. So let's focus on Z. In simulation, it's perfectly random element in the domain. What is the marginal distribution of Z in these accepting executions with an honest prover? And you can see that there is a random in D, because no matter what's this witness, no matter what's the challenge, X prime was picked independently. Here is the honest verifier assumption. For the cheating verifier, C might have been computed as a function of Y prime. So this argument would be more complicated, Well, basically, we cannot argue. No, sorry, it will not exist, this argument, because we cannot argue full zero knowledge of this 3-round proof system. But for honest verifier, when C is chosen truly at random, and we just fix it in the argument, because we're arguing for all challenges C, Z marginal distribution of Z is independent by the fact that X prime is chosen in the domain and the fact that this is a group. So this operation is a one-time pad in the group. So it doesn't matter what C and X are. Okay, this is really just a generalization of the argument we've already had. Okay, but now noticing that the fact that you are not taking X by itself, but some function of X does not matter. Everything rests on X prime being a one-time pad, which masks this information. And so let's check special soundness. Okay, so not the best. Yeah. Okay. Okay. Well, let's try to do this on this piece of paper, because here we have both what the special soundness is, and we have the proof system. So hopefully we can fit the argument in this small space. So let's check. We should check that for every statement, okay, it's X in this view where we denote statement as X's, it's Y for the specific case. Sorry, for every first message of the prover, it will be Y prime. For every interaction CZ that is accepting, and for every alternative interaction which is also accepting, and assuming the only thing that these two are different, then let's see what follows if both CZ is a challenge response tuple that leads verifier to accept, and C prime Z prime is also such tuple. So what would have to be if they are both accepting? Okay, well, so if the first one is accepting, then you know that FZ is Y prime times Y to the C. If the second is accepting, then F of Z prime, right? So let's parse this statement. So the response C prime is accepting for challenge C prime with the same statement and the same commitment of the prover, which was A in here. So this must be equal to Y prime times Y to C prime. Okay. But if these two equations hold, then this is a group. So let's divide FC over the left-hand side. And what happens if I divide the right-hand side? Well, what happens is that Y prime drops out, which was also the basic of soundness for the bit challenge version of these problems, right? This random new statement, random graph, random point in the range of the one-way function dropped out, and we could argue something about the permanent statement. This will be the same here. Y prime and Y prime drops out. What did I divide? I divided this thing by this thing. So I will have Y to the C, well, minus C prime. right? Because I divided this by that. And now from this, is it still part of the piece of paper? Yes. So because it's a group homomorphism, so division in the target group corresponds to subtraction in the domain group. So this must be equal to f of z minus z prime. Okay, and this is y to c minus c prime. Now, because it's a prime order group, ZQ, then these have inverses, multiplicative inverses mod Q. So this implies that Y is an F of Z minus Z prime. But now I take the whole thing and I take C minus C prime and I look at its multiplicative inverse mod Q. So here I strongly assumed, right, that D is, okay, well, it didn't really matter that it's an additive group. What matters is a group, and it's a group of prime, but what matters is a group of prime order. So the fact that this is a prime order meant that inverses exist. Multiplicative inverses exist, right? So in other words, that this domain was really a field. So you can both add and multiply, and there are multiplicative inverses of everything except of a zero, which you get because you assume that these two are different. So C minus C prime is not a zero, okay? And this thing will also be a problem in the RSA case, okay, where the domain in the RSA case would be Zn, or maybe Z of phi of n, depends what exactly function you have in mind. But either way, they will not have prime order, and if C minus C prime have common factors with phi of n, then this inversion will not be true, and this will create issues. So these nice sort of clean properties, we will argue, have to argue relaxed versions of those. But in a prime order group, this inverse exists, so therefore this is the same as F. What was exponentiation in the target group? What did it correspond in the base group? Well, we had an additive relation for the base group. It corresponded to a multiplication, whatever this beta is, and it is C minus C prime multiplicative inverse mod Q. That's the beta. So in the base group, domain group, that corresponds to multiplication. So this is F of C minus C prime minus 1, and it's mod Q, but I will not carry this, times Z minus Z prime. So that's it. This thing is your X. Right? So this is a domain element whose mapped by the function f into y, and therefore y is in the language, which is exactly what we wanted to argue, right? So the statement is in the language the minute that there exists two for that statement and any first message of the prover, there exists two interactions which are both accepting, which was this constraint and this constraint, and they have a non-equal challenge, because that's all we needed for this to have a multiplicative inverse, and therefore for this preimage to exist.
Professor?
Yes.
I can see that in this case you only need two valid challenges, but is there a similar definition for more than two? So special soundness with more than two.
You know what? No, because basically, you know, maybe someone proposes as a technical thing to argue. Wait. Well, I mean, wait. I mean, well, if there's that you need a bunch more from which, so you need the statement to be true on say 3 interactions for this. Yeah, so effectively, that's how you argue for the cases like RSA, where you need more of these interactions to assure that you will have a bunch of differences between challenges, and you know, perhaps if one of them are not coprime, then the others will be effectively forced to be coprime. Okay, but I'm not sure that these arguments precisely go in that way. But okay, something like that, because the arguments basically have to repeat more times in order to get the truly negligible soundness. Now, okay, why does this? So we only argued the special soundness property. How come we got negligible soundness error as a consequence? Well, we did get it in the consequence. So that special soundness implies this if ZQ is large. Okay, because so let's assume that Y is not in the language, and let's just see what is the probability that any cheating prover survives this. Okay, and I will argue that the probability is negligible soundness error, and it's in fact simply 1 over Q. Why is the soundness error only 1 over Q? Because if Y is not in the language, then no matter what the first message is, there exists only one C on which the prover will be able to respond. Because by this statement, if there exist 2 different C's on which the prover can respond, so for which there exists Z and Z prime respectively, on which the verifier will accept, then the statement must be in the language. So if it's not in the language, then there must exist only single challenge for which the prover will give a satisfying answer. But if that is the case, and the verifier chooses C at random from ZQ, so that means that for every message Y prime that the cheating prover sends, there exists a unique C for which it can respond. So as long as the verifier does not choose that C, there is no response. Or otherwise, this thing would kick in and you would have that the statement is in the language. So that's why the soundness error is just 1 over Q. Okay, and it's implied by special soundness, but it's implied provided that the space of the randomness of the verifier is ZQ. Well, but it is in this proof system. Okay, so I'm adapting it to this particular additive domain group, which fits my applications. you can extend it to other cases. Like, for example, the challenge perhaps is a pair of so we'll see extensions where this, this would be more complex. Okay.
Wouldn't C always be 0 in this case?
What is 0? What
C.
could be?
So if C is, because C equals 0 would work.
Yes, so C0 corresponds to the what we called B equal 1. So it was a case where the verifier just asks the prover to explain X prime. So we explain this statement.
Right, yeah.
Yeah.
I think
so
the problem is that the prover
choice,
is not
still included
honest
here.
anymore.
Yeah. So it's still possible.
Right, yeah, I meant like I meant that C equals 0 would always be possible for the prover, but the prover may not send a real Y prime.
Yes, yes.
So maybe he can't answer with C equals 0.
Right?
Okay.
But no matter what he does in this target group, because of the homomorphism, if this equation is satisfied for 2 different C's, then this kicks in and you just compute the witness. And not only the witness exists, but in fact, you can efficiently compute it. And we'll revisit this property in a notion of extractor from a zero knowledge proof. Okay. Okay. So now, so let's see. So the what? Okay. And did we increase the cost? Not really. So what's the cost of this Sigma protocol for the language of homomorphic function images? It's both prover and verifier apply compute F. Prover on X prime, verifier on Z. But that's it. The rest is well, it's some operation in the base group, some operation in the target group. If this is an exponentiation, then of course this is there is an exponentiation here, but this is a cheap operation for the prover. If these are group homomorphism, then these are exponentiations basically, right? In this case, so the cost is here, and typically these costs can be combined. So these are not 2 separate operations, but they can be put together and computed jointly. Okay, so what's wrong with this thing still, right? Okay, it's 3 rounds. We would like this to be fewer rounds still, but that's not crazy that you have a little bit of interaction. What's wrong is that it's an honest verifier zero knowledge. So we don't know if this is zero knowledge for any cheating algorithm. So here is a random oracle model compiler from Sigma protocol for L to non-interactive zero knowledge proof for L. Okay. So how did so here again we have Sigma protocol notation on statements, and the witness you send. So let PV be as the Sigma protocol, for L, assume let RV be the space of randomness of the verifier. Okay. In the language, in the Sigma protocol for languages of homomorphic one-way functions, for function images, randomness of the verifier was the randomness was, whatever is needed to sample random elements from the domain group. But the compiler is more general. Whatever Sigma protocol you had, let this be the space of the verifier's randomness. And because it is prover sends two messages, so let P be specifies at P1, P2, where P1 given X, W, and randomness of the prover outputs the first message A, and P2 given X, W, randomness of the prover, and the challenge gives the response Z. Okay, where RP is the randomness of the prover. So C in this. So what about the verifier? And let V be stand just for the final verification, which the verifier does, because the way that V computes its message is just samples at random from this space. So we don't really need an algorithm for it. In other words, what we will call the verifier is just a procedure that takes the statement, the first message of the prover, the coins that it used for the challenge, which were randomly generated, the response, and outputs 0 or 1. Yes. Reject or accept. Okay, so that's our notation. So now consider the following proof system. P prime, V prime. So we'll modify these algorithms into new ones, where both interact with hash function H, where H maps whatever, okay, onto the space of the randomness of the verifier. Okay, and we will model this hash function as a random oracle in the security argument for this proof system. Let's now first. So this is a ROM compiler that we are drawing. Okay, so this is what we assume what we have. This is what we are going to construct. What does P prime do? So P prime on X and a witness picks the randomness of the prover at random, runs P1 on the stuff to get the first message. Now hashes using the statement and the first message to get the challenge of the verifier, or well, you know what? I will use notations that I'm more used to. So he computes A as an output of P1 on XW and the randomness, computes C as an output of the hash function on these inputs, and computes the response Z, which the underlying prover would have computed if you fed him this response. And V prime outputs just a single bit string, let's call it pi for a proof, A, Z, as the non-interactive proof that X is in the language. Okay, let's see what the verifier does with this stuff. So the verifier, by verifier, I just assume the final verification algorithm, right? So let's, okay, no, sorry. That was the underlying verifier of the 3-round proof. So let's see what in the new proof system, what the verifier does. He has the statement, and he gets the proof, right? Because it's now a non-interactive thing. The prover locally generates a single message, pi, which just has both A and Z all together in it. The verifier gets, he knows the statement, and he gets this string pi, which parses as AZ. And he will output 1 if the underlying verifier, given the underlying verifier takes the statement, the first message of the prover, and the challenge, and the response outputs 1, but this challenge is undefined, for challenge, which is computed as hash of XA. Okay, so the verifier recomputes the same challenge that the prover computed, querying the hash function on the statement and the prover's first message A. So if and if, and V prime outputs 0 otherwise. So the new proof system looks like this. They both interact with some hash function in the sky, okay, the hash function as described here is not exactly in the sky. They both have, it's an algorithm that both the prover and the verifier can compute. But in the security argument, we'll only give the security argument for the case that this hash function is a random oracle, so it's really external to both of these prover and verifier algorithms, and it can only be queried as a black box. And in that world, really, or a model of the world, what the prover outputs is a single message pi, which is implemented by this AZ pair. And the verifier on this single message outputs accept or reject according to the procedure. The difference between the proof system that we started with, that was the Sigma protocol, and the new one is that both parties compute the challenge non-interactively, so to speak, right, by querying the hash function. intuition for why this is a fully zero knowledge is the following. If well, first of all, why is okay? Why is the zero knowledge for arbitrary cheating algorithm? Because in here the verifier didn't choose. So consider an arbitrary cheating algorithm here. Well, he doesn't have much power, does he? He just gets this pi string. He cannot even send some maliciously formed message to the prover. The protocol doesn't consider this, right? It's a one message protocol. What verifier can do is to query hash function. And perhaps by these queries will disable the simulator from constructing this. How did the honest verifier simulator work? He picked the prover's challenge, the verifier's challenge, and was able to, for that challenge, simulate. And now he will do the same and embed the challenge that he picked into the hash function outputs. We'll have to see next time that this really works, but this is the intuition. What about soundness? Why did it not destroy the soundness? Because we clearly eliminate, reduce the power of the verifier, but by the same token, increase the power of the prover. So perhaps even if he couldn't cheat here, he now can cheat. Well, not really, because if this is a random oracle indeed, then no matter how many queries prover makes, these outputs are random at every case. And note that what he sends to the hash function is both the statement and the commitment message. So if it's not in the language and there exists only one accepting path, because if there exists two, then it would be in the language, the only way of the prover to manage to cheat is to count that the C that the hash function outputs will be that unique one that exists for this X and A pair. And that's of course 1 over space of the verifier's randomness. So the size of that space, right? So this will be strong sound. The soundness will be a function of the size of the space. Okay, so we're running out of time, so we will do the formal of this next time, or yeah, I'm not sure. Perhaps I will just draft it for you and send to the notes. So just to finish, we'll claim that P prime V prime is a full zero knowledge proof with negligible soundness error in the random oracle model, as long as the space of the verifier's challenges is super polynomial in the security parameter, right? So he can only make polynomially many queries, but the chance that each one of them falls to that unique one is larger than the polynomial. So the end result of that attempt is still negligible. Okay. So minus the fact that, you know, I didn't prove this formally, do you have some questions?
No, I'm good. I think it's, from what you said, it should be easy.
All right.
To formalize.
Okay. Okay. Yeah. Okay, but we will still see it. You know, the reason is that it's worth seeing is that also we will actually argue a stronger property called proof of knowledge. Not just zero knowledge proof, but the zero knowledge proof of knowledge, which is a strengthening of and that is a useful property in practice. In particular, it implies signatures. And it implies security of like security signatures that are used in practice. So, okay. So see you next time.
See you.